Okay, we're going to pick up where we left off, which was taking quadratics and factoring them. However, we've done only quadratics so far that have a leading coefficient of 1. Even if they didn't have a leading coefficient of 1, you found that there was a GCF that factored out and then left you with a quadratic that has a leading coefficient of 1. So today we're going to expand it a little bit and start looking at quadratics that don't have a leading coefficient of 1. However, before we go to that, there's a couple other terms I wanted to talk to you about. Have you ever heard this word before? Or this word before? Binomial. Bi means what? Two. Nomial means?
Number.
Terms. Yeah. Binomial. 2 terms. Trinomial. 3 terms. Right. So a binomial would be something like x minus 3. Okay. It's a expression that has 2 terms in it. A trinomial would be something like x squared plus 2x minus 3. 3 terms. So what we did the other day with factoring is we took quadratic trinomials and broke them into the product of 2 binomials. Okay? Every one of those quadratics that we factored had an A term, had a B term, and had a C term. We're going to start today by looking at quadratics that don't have a B term. Okay, these are very special quadratics that pop up every once in a while, and they are called the difference of perfect squares. Gracias. What does difference mean? I'm sorry? Minus, correct. Is there a reason why you answered that from the... Oh, you're blowing your nose.
Yeah.
You don't want to blow your nose in front of everybody?
Yeah.
Don't be shy.
He always says that.
I just want to roll up to him and be like, hey kid.
Jack. We're at JFZ here, buddy.
JFZ?
Anybody? JFZ?
No.
Judgment-free zone. There you go. Loud and proud, my man. There we go. Just what you all wanted to see in the morning. Jack blowing his nose. Good job, Jack. Okay, so difference of perfect squares. As he mentioned from the hallway, difference is subtraction. Perfect squares are perfect squares. So now instead of having a trinomial that we're factoring, we're going to have a binomial that's still a quadratic, but they have to be perfect squares. So something like this. Okay. Notice, no B term. Gone. And the 2 terms that are left, one is the quadratic term and one is the constant term, both of those are perfect squares. Okay? If you have that special scenario, it factors very nicely. And it factors into the following. The square root of the first term, what's the square root of x squared? X. Square root of the first term minus the square root of the second term. 7. Times square root of the first term plus square root of the second term. Correct. Okay. That one's not bad. They will get more complicated. For instance, let's change colors on this one.
Oh my gosh.
Now, a couple mistakes that people make when doing this is they will realize that you're missing a B term, so you'll automatically think it's the difference of perfect squares. Or that sign in the middle will be addition, and addition doesn't work. The sum of perfect squares doesn't factor. Now, this is getting outside our comfort zone because that's not a quadratic, but do you all see that those are both perfect squares?
Yeah.
Okay, good. What's the square root of the first term?
2x to the second power.
Minus square root of the second term. 3y times square root of the first term plus Square root of the second term. Done.
Easy to know.
Okay? So again, no b term with perfect squares. We get that. Okay? Beautiful. But what we want to do is look at quadratics that have all three terms, but don't have a leading coefficient of 1. So we'll start with something straightforward. 2x squared minus 5x minus 3. Now all of a sudden my leading term is 2 instead of 1. We have to take a little bit different approach to it. Actually, correct that. We're going to take the exact same approach to it. It just requires a little bit more work. This is where the OI term becomes very important. Okay, so same thing. We're going to take a quadratic trinomial and break it into a product of two linear binomials, just so we get all the terminology correct. Same thing we did yesterday. Well, first of all, what's the first thing we should check for? Good. Gray's common factor. Okay. Perfect squares don't apply here because we got a b term. Is there a GCF in those three terms? No. So we're going to go right into factoring. The same process we used on Monday, we're going to use here. We have to figure out a way to break down 2x squared as a product of two terms. What would that be? So, say again?
2 and 1.
There you go. 2x and 1x. Is there any other way that I could break that down? I mean, other than 2x squared times 1. That would be ridiculous. What's going to make this more difficult is when we get to leading coefficients that have a lot more factors. And you'll see in my second example that it can get a little bit nasty. This does at some point become a guess and check system. And you may have to use an eraser. Well, not a digital eraser, if you will, because digital. All right, now we do the back term. Will my signs be plus, plus, minus, minus, or plus, minus?
Plus minus.
Plus, minus. And now, because the leading terms aren't the same, the plus, minus locations matter. So, Sean, what do you want to try? There's no wrong answer here. You want to do plus, minus, or minus, plus?
Let's do plus minus.
Plus, minus he's going with. I love it. Okay. Factors of 3.
1 and 3.
Any other possibilities?
That's it.
That's it, 1 and 3. So now you have to decide, Sean. Would you like to put the 1 there, and the 3 there, or the 3 there and the 1 there?
Let's do the 1 and the 3.
1 here,
Yeah.
3 here. Beautiful. Okay, now we're going to check in a second. See if he's right or wrong.
So good.
First term's good because we know how we broke down 2x squared. And 2x times x, 2x squared. The last term is correct because 1 times negative 3 is negative 3. Now, this is where the OI term becomes important. 1 times x is x. Negative 3 times 2x is, I'm sorry? Negative 6x. Is negative 6x plus x is, dude.
Let's get it.
Nailed it. Negative 6x plus x is negative 5x. We are GTG. Good to go. Okay. Now, what if it didn't work out? Well, I'm going to continue with the pink here. Let's suppose he said, oh, let's put the minus here and the plus here. I mean, aside from us just laughing right at him, when we do the OI, we would have negative x and 6x, and 6x plus negative x is positive 5x. No good. What's wrong with...
Sean made a mistake.
Why did that just happen?
Because you touched it with your arm.
I didn't.
Yeah, you see that stuff is sealed.
It's just my magnetic personality. All right. Got it? So at some point, this does become a guess and check. And you might put some values in there and it won't be right. Now, what's not going to be right about it? Maybe you have the signs in the wrong location. Maybe you broke down the numbers in and I wouldn't say a wrong way, but in a way that's not going to allow it to be factored. Okay, so let's try one. Let's ramp this up a little bit.
Goodness gracious, that's a big number.
Okay, now the reason this is going to be ugly is twofold. Number one, 6 can be broken down a lot of different ways. 6 and 1, well, not a lot. 6 and 1, 2 and 3. 12 can be broken down a lot of different ways. 1 and 12, 2 and 6, 3 and 4. Your job is to figure out how the puzzle pieces all fit together. Go. Try it.
Approximately different problems.
Go get them.
I'm gonna go for breaking our sense. I'm gonna go 2 or 2. Yeah, I'm gonna be and then you go 3, 4, you go 1, 6, and then you go 3.
I'll go with 3. Wait, guys, the repulse and turn in are like test question 2 actually.
Plus minus,
No. Oh, it's definitely,
It'd have to be.
That's -6.
Question? Wait.
This is 9.
Ask them to make sure, have them check it to make sure you're right. I don't want to waste time with wrong answers. I'm a mover and a shaker here.
Okay.
4 and 3, 2.
3x minus.
I know.
No.
Wait, 6. I was right.
okay, it's not.
It's not.
Wait, do yours.
It's not 3. I got it. So it's -8. That's positive 9. I can get it. I got the first time. 3x plus -2x is 1. I would write the first time. Here, I did x.
6x.
And then 9x plus
Oh, that's what I did.
Negative 3 times 2x.
See if I can see I don't see her. She must be hiding.
Oh, so you check.
For example, I multiply these two together, I take the factors that add up to this. So then so this will work.
Yeah.
And then you solve for that. This becomes its own separate equation, and this becomes its own equation. You take that greatest common factor here, and then these two equations should be multiplied. That's one of your equations, and then this plus this should be your
That's what I did last week, but I couldn't get through all of it, so.
It's the only way I remember it. I can't do that.
I don't know.
Okay. I got -9.
I got -12. I got it correct. So.
Wait, do we have the same answer?
Yes.
All right, let's go. Jacqueline, 6 and 1 or 2 and 3? Yes?
Yes.
Yes.
2x, 3x, or 3x, 2x?
2x, 3x.
Does it matter?
Yes.
Yeah.
Yes.
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 Is A times B the same thing as B times A?
Yes.
Oh,
Yes.
not in this case.
That would be yes.
Because it's apple.
Sorry, Jacqueline, back to you. Did you want a 3x here or a 2x? 2? Okay, that's fine. All right, what are the signs? Plus, plus, minus, 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 plus, plus, minus. Plus, minus. How'd you break down 12? 3 here, 4 here. All right, there's a proposal on the table. Let's check it out. -4 times 2x is -8x. 3 times 3x is 9x. 9x plus -8x is positive x. Let's go! Nicely done.
We are so smart.
Now I will tell you, one thing that will frustrate you is if you forget about 3 pesky little letters.
A, B, and C.
No. G, C, and F.
Oh, wow.
So imagine if I gave you this exact same problem, but it said the following.
What's different?
And you tried to factor that. So look how you can break down 36. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6. However, if you just factor out a GCF, in this case it would be 6, then you get the problem at the top in blue, which is manageable. Now, does that mean you can't factor that? No, that thing would factor. But if you factor a GCF problem, when you're done, one of these binomials will have another factor involved. So when you're done with the problem, you might want to take 2 seconds to look at those binomials and see, do they have anything in common? If they do, they need to be factored out. Or the best way is to just do the GCF at the beginning. Got it? You can do this, right? Outstanding. Okay, so